This webcast discusses the lab for the unbalanced net force, and we're going to use one of the University of Colorado PhET simulations, the one called Forces in Motion. There is a link to this PhET provided at the top of the lab handout. When you click that, it will take you to this page, and we want to use the part of this simulation called acceleration. So double click on that icon on the right. It'll take you to this screen. Read each of the steps of the lab and follow them closely. And so you'll notice that I've just done step 2. I click the acceleration. Then I want to check the boxes for forces, sum of forces, values, masses, acceleration. Then I want to change the mass on the crate by piling some objects on top of it. You can choose whatever objects you want. In my example, I've put the man holding a water bucket. Okay, and so I've stacked these 3 objects. I'm going to add up their total mass. 50 plus 80 plus 100 is 230 kilograms of mass, and I'll record that here at step 4B. Now it says move the value of friction to a very small value, but something larger than 0. This is important, the larger than 0. So the way I do that, on this, we've got this rocker switch that goes from none to lots of friction. I'm just going to slide it close to the, not all the way over to the left. No. We want some friction, but just not a whole lot of friction. So I'm going to leave it over here, somewhere close to the left. Okay, so then I'm going to choose a small value of applied force. I'm going to just click here. The first value I get is 50, and look at what's happening. I've got 50 newtons of applied force. The orange man is pushing with that much force to the right, but friction force is the same amount, 50 newtons, pointing to the left because it's opposing the motion. And so my sum of forces in the horizontal direction is 0, and so my acceleration is 0. The object, the crate, is not moving. And so I want to summarize that in step 8. And to say the crate remains motionless. I'm also going to record this value of force, this net force, and this acceleration in table 1, which is at step 20. So I'm going to race down there to step 20, and this will be the first row of my table. I applied 50 newtons of force, I had a net force or sum of force of 0, and an acceleration of 0. Okay, I'm going back up to step 8. Okay, now I'm at step 9, where it says to draw a quantitative force diagram for the crate, and so I'm going to do that. I'm going to show the forces due to the crate, its weight, separately from the weight of the man pushing down on the crate and the weight of the water bucket pushing down. Okay. Then I'm going to write an equation to find the net force in the vertical direction. So since the crate is not moving up or down, the sum of forces should be balanced in that vertical direction. There should be as much force pulling up on the crate as there is pushing down on the crate. And so I can use that fact to find the normal force that the track is exerting on the crate. It's going to be the sum of these 3 forces pushing the crate down. Okay? And then I'm going to do a similar thing to find the equation for the net force in the horizontal direction. So the orange man is pushing to the right with 50 newtons of force. The friction is pushing to the left with 50 newtons. Those are the only 2 horizontal forces, and so they add up to 0. Okay? So in both directions, vertical and horizontal, the net force is 0. Okay, now we get to an interesting part of the lab. We're going to gradually increase the applied force 1 newton at a time until the crate begins to move, and we're going to record the minimum value of applied force, which results in a non-zero sum of forces. Okay, so I'm just going to increase 1 at a time. I'm using this little arrow. Okay, notice that as I increase my applied force, my friction force is also increasing. Look at this. Okay, I've gone up to 70 newtons. The applied force is 70, the friction force is 70. The crate is still not moving. Now I'm going to go a little slower. Okay, so I'm up to 117 newtons of applied force. Friction force is also 117. Every time I increase applied force, friction force is also increasing. And so the forces are remaining balanced and the crate is not moving. Is this going to happen forever? I'm gradually increasing. He's setting his feet. Did you see the little... Oh! Look, now it's moving. I finally have a situation where the applied force is 130, and that's bigger than the friction force. But look at the friction force. I know that I had a friction force of 117 just a minute ago, but now it's only 96. Okay, so I want to record this situation in my table. Okay, so first of all, I have 130 newtons here. And then I'm going to go down, and in Table 1 at Step 20, I'm going to say, oh, 130 newtons of applied force gave me a net force of 34 newtons and an acceleration of 0.15 meters per second squared. So that'll be the next row of my table. Okay, then it tells me to reduce the applied force 1 newton at a time until the applied force just balances the friction force. Okay, so I've got a friction force of 96. Let me start decreasing the applied force. It's at 130 right now. Let's say 129. Okay, I'm going to keep going down until I get to 96. Okay, so now I have an applied force of 96, a friction force of 96, my sum of forces is 0, and my acceleration is 0. Okay, and so I want to describe what happened here. The crate moves at a constant speed when the net force is 0, right? So it's moving at a constant speed. There's no acceleration when the applied force is balancing the friction force. And so we're going to do a force diagram for that situation. And, okay. So both of these situations, the crate was at equilibrium. And so you should go back to Unit 4 and look up the meaning of equilibrium. What does that mean, right? Equilibrium describes a situation in which all of the forces acting on an object add up to 0. Or in other words, the net force, right, the sigma F is 0. And then review Newton's first law of motion and write it here in your report. Remember, there are two scenarios where an object is at equilibrium. One is when the object is at rest. It will remain at rest unless it is acted upon by an unbalanced force. But the other situation of equilibrium could be an object in motion that continues moving at a constant velocity. That means a constant speed in a straight line. So neither the speed nor the direction are changing. And so it will remain at that condition unless it's acted upon by an unbalanced force. And when we talk about unbalanced force, we're referring to a net force that does not equal 0. Okay. And then the final thing, then we want to talk about all of the forces acting in this situation. So we've got the forces that are being exerted on the orange man. We've got the forces that are being exerted on the crate, and we've got the forces that are being exerted on the track/earth. Okay, and so you need to do 3 force diagrams, one for each of those objects: the man, the crate, and the track/earth, and as you identify all of the forces in that situation, use little symbols to identify which ones are paired together, which ones are the Newton third law pairs. We've done this several other places. You may want to look at worksheet 4B, question number 16. That was the grocery cart. This is in Unit 4, worksheet 4B, question 16. Also, worksheet 4C, the next worksheet, number 2, we identified all of the Newton third law pairs for 2 blocks sitting on top of each other. And in both of those locations, we talked about Newton's third law and identified the 4 criteria that must exist when we're identifying Newton third law pairs. And so you want to record that here at step 19.